Okay, let me just finish up soldering fairly quickly. Last time we talked about solderability testing is empirical, and we also said that solder jobs below about 3 millimeters in diameter, which is about 1/8 of an inch, have shapes that are controlled by surface tension rather than gravity. And that's actually an important thing to recognize when we get to any type of liquid metal is going to want to turn into a sphere or be held in position by surface tension if it's smaller than about 1/8 of an inch. And when we get to fusion welding, that gets to be important because, you know, some of those weld beads, are, if they're much bigger than 1/8 of an inch, they're going to fall with gravity, right? But if they're smaller, a small weld bead will stay in position in the joint, even if the joint's overhead, as long as the weld bead is small. Now, it might be that it's a little bit bigger than 1/8 of an inch, because that's an approximate 1/8 of an inch. But also, even if I'm welding overhead or soldering overhead or something, and the thing slumps a little bit by gravity, that's not necessarily a big deal. You know, it's just if it falls out in your face, that is a big deal. And so if it gets to be, you know, 2 or 3 times that 3 millimeters, well, then it is going to fall by gravity, and gravity forces will dominate. But basically, somewhere around 3 millimeters in size is where gravity forces and surface tension forces are approximately equal or so. Okay, I only want to cover up, yeah.
In practice, like how do they control how much bead they're putting on there?
Well, there's 2 ways to do it. If you're doing surface mount technology where you put your silk screen of solder paste, you essentially control the thickness of the solder paste you put on, and you're putting it on in a little pad. Okay, you've already put etched copper pads onto the printed circuit board, and you're going to screen print a certain thickness, and they actually have a doctor blade. A doctor blade is just a scraper that controls the thickness of something. And they can take they'll scrape it and they control the thickness, and that controls the amount of solder. In a what they call a reflow operation, where you have this weir of hot solder going over a dam, and you're going to go through there, essentially, the circuit board's a little bit colder, and it will freeze on there as much as it can. And so by controlling the temperature and the flow, the solidification rate of the solder, you can determine whether you get too much solder or too little solder. So controlling temperature of the board, it being colder than the solder bath, it's a heat transfer problem and a speed going through there and everything else to get the right amount. Now, how much actually sticks on also is a function of how well the fluxing is working. So there's lots of parameters, but basically you kind of, in a reflow operation, you're hoping that surface tension will take care of it, and heat transfer, okay? Balancing heat transfer, and then surface tension will hold it, because typically you're going to have a little wire sticking up through the circuit board, and you want surface tension to kind of form a nice fillet around there. It's not going to form too much, and the rest of the liquid will kind of fall off. You'll form a nice little meniscus just by surface tension. So one of the problems, well, actually, we might as well talk about it now, I guess, since you're asking how do you control how much alloy you use. Let's say I was making a soldered, not a printed circuit board, but a pipe joint for some plumbing. And so here's one pipe, and here's your union that you want to weld, or not weld, but solder on here, right? You can imagine that's just a pipe right down here. So here's where I want to flow the solder inside this little gap right in here. Okay. Well, typically, one mistake that a lot of people do, and actually I've seen a number of floods caused by this. One of them up here at the Charles Hotel. If the guy's not experienced in soldering, a lot of people will essentially put their torch, their flame, right here, and heat up this corner, and then they'll put their solder right into the flame and melt it on there, and they'll get a nice little fillet, just like that. But they won't get any flow down here, where you want the flow, because the solder joint is not anywhere near as strong as the base copper. I mean, it's solder alloy. It's near its absolute melting point. It'll creep. In fact, typically, it won't take more than about 1,000 psi as a shear stress. You know, and metals will take, 20,000, 30,000. The solder, because it's up near its absolute melting point and could creep under high stress, 1,000 psi is about the highest stress you want it to have. In order, you really want the solder to flow down here. And so the typically a plumber will come in here with his little brush and he'll paint the male, and then he might paint the inside of the female with some flux. It's a little kind of pasty flux. And he'll slip the two together and he'll start heating it up. And the proper way to heat it is to heat back here with your torch, with your flame, and heat over here. So the heat flows over here. You're not trying to heat right where you want the solder to flow. You're heating back here to overheat the copper so that you get enough heat here so that when you finally get to the point where you put your solder drop here, you actually see the flux kind of bubbling out and stuff. And then you put your solder here. You're not hitting it, you never hit the solder or braise directly with your flame. You basically let conduction from the hot base material. If the base material is hot, that solder is going to wick down here by surface tension into this small capillary. Okay? That's the way you're supposed to do it. An even better way to make the best solder joints with no flux and no problems of corrosion from the flux would be to make a wipe joint. In a wipe joint, you basically take your tube and you paint some flux on it, and you don't assemble the two tubes, one the male inside the female. You basically heat the thing up same way, and you put your solder on there, and you pre-tin the surface. And they call it a wipe joint. You take a rag, because this is relatively low temperature. If you're clever, you'll have gloves on too in case the rag slips. But you basically wipe any excess solder off the joint, and you pre-tinned that whole thing. And now you can clean all the flux off of it. You've now got a piece of tinned copper. And you can do the same thing on the inside, on the female piece, and they wipe it. And then you now have two pre-tinned pieces, and you butt them together. That's why you had to wipe the joint, so that because of small clearance, if you left a blob of solder in there, they wouldn't go together after it's solidified. So you make a thin wipe joint on each one of them. You slip them together. Now I don't need any flux, because I'm just going to melt my solder together, and I take a little bit of extra solder to flow in there, and that's the best joint. Now, I actually hired some plumbers to replace my furnace about 10 or 15 years ago, and I came home early to see how they were doing, and they were actually making wipe joints, which means I knew I was getting good quality work. Most plumbers I've seen do it, they just slap that flux in there and stick it together and let the solder flow in. Okay, and that's the way I usually do it too. That's fine, you may leave some flux in there. And the flux can be corrosive. I had a situation once on a marine tanker where they were transporting asphalt in these barges, okay, and so they had to have these heating coils to heat up the asphalt so that you can pump it out when you get to wherever you're going. You can pump it in, but then when it solidifies, it's kind of hard to pump it out afterwards, right? So you have to reheat it when you get to the unloading dock. And these were aluminum bronze tubes, and they were brazing them together, and they were getting cracking because the flux, the residue that was left on there, in that case, caused stress corrosion cracking of the aluminum bronze. And so the flux can create problems like that. And then a lot of times, I've seen problems in copper water systems where leaving some flux on there, sometimes you can get some corrosion problems. Usually you got so much water through there, it kind of washes all the flux away eventually. It's not a problem. But there's another way to do this, and this actually, since the majority of you here are Navy people, although you're surface, not subs, the thresher, okay? It was in 1962, 63, the thresher. I was living in Virginia Beach, Virginia at the time. In any case, or actually maybe just after that I was living, I guess it was just after that, but anyway. So the thresher was a nice new nuclear submarine. It was on a controlled deep dive, and it had a sub-tender above it. And they lost power, and they tried to blow their tanks, but they were so deep that when they didn't have power to get back to the surface on their own, because they had a flood in the reactor compartment. So they lost power, and they tried to blow their tanks with the compressed air they had, but they're so deep that the compressed air couldn't blow enough water out of the tanks because the pressure was too high, and the compressed air didn't expand enough to completely blow the tanks. So they got an upward momentum, and supposedly they got within a few hundred feet of the surface before they just started going down, and they were negatively buoyant. And Admiral Rickover was head of the program at the time, and the whole Navy had it was big, huge culture change for the U.S. Navy. And they had something they created, the SubSafe program, and they almost quit building submarines, I think, for about a year and a half. And they just, all those people spent time figuring out how to make everything ultra safe. And in fact, the Navy at that time was about 15 or 20 years ahead of American industry in terms of quality of construction and everything else, because they just spent a year and a half, 2 years just figuring out how to make things perfect. And what they think happened on the Thresher is it had just recently been constructed, and they had a braised joint. And in fact, they believe that the braised joint had that same problem I just talked about. You got a tube within a tube, but this was a seawater plumbing system. And apparently the guy who had brazed this in the shipyard actually put the torch right there on here, melted the stuff, and they never got any flow down the thing. Now, I don't know if the Navy really learned that or they surmised that, deduced that. I don't know if they ever recovered that. It was all classified. Okay, but the story was, well, the reason we know this, I know this story, is because in the SubSafe program, when they tried to fail-safe things, they basically changed the system so they put a little notch in this one, and they would pre-place the braze alloy as a little ring inside that groove on the inside. And now all the guy had to do was heat up the outside and wait until he saw metal flow to the outside. That way you knew you had a joint, okay, by visual inspection. And that's kind of the type of thing we call Six Sigma robust design or things like that now. But the Navy figured those things out back when they had this catharsis of going through, you know, the loss of the submarine when you had the tender right above it and there's nothing they could do. Okay, that's if you go into a shipyard now and they're brazing piping, you will, in a military shipyard, you will usually see them using that technique. More expensive, but you know you've got a joint. Okay, and like I said, I haven't worked on a solder joint causing a flood like that since last week. Okay, you know, where we're not one of these, but one where they just got a little fillet around here and it didn't flow down any further. I probably worked on half a dozen of those over the years where they're not as strong as the ones that it flows all the way through. I wanted to throw this up. This is kind of a nice plot, which you may have heard or seen this type of information before. But it's the repair costs on a logarithmic scale and this came out of one of the soldering books, but it's generally true of almost anything if you're talking about whether you're talking about repair of an instrument or something. In this case, for solder, before soldering, doing some visual testing, inspection will cost you less than $1 to inspect things. After you've actually made the solder joint, it's going to cost you about $10 to fix it, okay, because now it's a manual operation. This could be automated, okay, you have vision systems and other stuff, inspect things and make sure everything's ready to go. This has to be done manually, and that's why it's almost, well, it's more than a factor of 10 increase in cost. If you find it in the system where you put all the circuit boards together and you're doing burn-in on this big rack of electronics, it'll probably cost you $30 or $40. You might be able to isolate it, but you got to take it out of the system, take it over and do the manual repair. And so it's going to cost you even more. If you have to go in the field, now you got to pay for someone to go out, you know, a day's time or whatever, to go out in the field, a technician to fix it. And so this is not just for soldering. This is typically how it goes in terms of the costs for repairing things. And it's one of the reasons why warranty repairs are so expensive. And it's better to build it right the first time, as far as that goes. Okay, the last thing I want to do on soldering, you guys have seen that type of data before? Of the cost, how costs escalate. So, okay, the last thing on soldering I want to go through is, I don't know why my secretary put my name on this, maybe. Turns out that soldering requires, we think of lead tin solders as, you know, being pretty robust, but and well, we make trillions of solder joints each year, so they are pretty robust, but it turns out the solder composition is fairly critical. Small amounts, like 50 parts per million of aluminum, magnesium, or zinc, will not be soluble to form oxide inclusions, or they'll form intermetallics. They can form oxide inclusions in there, and they make the solder gritty, and the intermetallics degrade the mechanical properties and the solderability. Antimony is actually added sometimes to 0.3%, up to 0.3% to improve wetting. Antimony actually has a stronger affinity for oxygen than lead or tin do, and so it will help clean that copper oxide off the surface. It's also reported to reduce tin pest. And tin pest, I've been told by some people in the soldering business that tin pest doesn't occur, and so you don't need to add antimony. Tin pest, it turns out pure tin has a phase transformation from one crystal structure to another at minus 18 degrees centigrade or something, which is like 0 degrees Fahrenheit. Actually, the transformation equilibrium is a little warmer than that, but the maximum rate is around 0 degrees Fahrenheit. And for example, during World War II, the Soviets had this big stockpile of tin, which was a strategic material, stored outdoors. And in the winter of '44, when it was nice and cold, they had, and all the snow melted in the spring, they had a stack of tin powder rather than tin ingots when the thaw came, because what had happened is the tin goes from monoclinic to triclinic, and triclinic crystals, basically the crystals just shear against each other, and the whole thing just rips itself apart as a brittle fracture and turns itself to a powder. Okay, and people supposedly have seen that in some soldering operations. Now, maybe they were soldering operations where they're using pure tin, and if you add a little bit of antimony, it will stop that. It'll inhibit the transformation. And so a lot of times people will add that to lead tin alloys that have other alloying elements. Well, it turns out adding the lead to the tin gets rid of it. So you don't need the antimony too, is what I've been told. But you'll still see that in the literature, that you add antimony to the alloy because of tin pest. Arsenic and iron have to be kept down to the 200 to 500 parts per million range to prevent intermetallic formation. Bismuth, similar to antimony, has a strong oxide, and it can help the wetting, so sometimes you add up to 0.25%. Cadmium, you want less than 10 parts per million because cadmium is not soluble in lead or tin. It segregates in the solder bath, and it creates a scum on the surface, dross. It turns out that gold and copper you don't want in your solder bath because they form intermetallics if you get to these 800 ppm levels. But in fact, gold's not usually a problem. If your solder bath gets to 800 ppm gold, it's worth sending it to the refinery and getting the money out of it, okay? But you will pick up gold. If you're soldering printed circuit boards that are gold-plated, then you will pick up some gold in your solder bath, and actually every now and then you do send these things out to the refinery, the whole bath of 1 ton of solder or whatever. Nickel is rarely found. Silver is sometimes used up to 150 parts per million, but sometimes all the way up to 2%. But you can't go much higher than that because intermetallics form. And the one I mentioned a couple of days ago was sulfur. 7 parts per million. You form copper sulfides on the surface. It's a strong contaminant. Most of your fluxes won't, they might get rid of copper oxide, but they won't get rid of the copper sulfide. And now you've just degraded your solderability dramatically. So, any questions on any of that? The last thing I wanted to talk about, see if I get the right formula. The right formula is right here. Well, I've said this, you have to avoid corrosion, and I've said that, well, I don't know how much I've really said, that you like to get rid of chlorides in particular. And the problem is that if you have lead oxide on the surface of something, and you have chlorides in the environment, that will react to form lead chloride plus H2O Well, the problem is that lead chloride will combine with CO2 in the atmosphere to give you lead carbonate plus hydrochloric acid. And so the problem with this little corrosion cycle is that it does form a cycle. You start out with lead oxide. That's on the surface of your solder joint just because the lead oxidizes in the air and forms a corrosion tarnish or an oxide tarnish. If you have chlorides present, any moisture, humidity is going to combine with those chlorides to form a little bit of hydrochloric acid in the moisture. That's going to form the lead chloride. The lead chloride then reacts with the CO2, which is in the air at about 0.3%, increasing it with time and melting all the icebergs and everything. Or not the icebergs, but the glaciers. And that will form lead carbonate, but it regenerates the hydrochloric acid, which now goes through and eats up some more lead oxide. And you end up forming this white powder. It's a white friable residue, and you don't see it so much nowadays because we don't have the same type of battery terminals in cars. We have the ones that screw in, whereas the old clamp ones, remember the old clamp ones that had the plugs? You ever seen a big white deposit on the anode, on the positive electrode? That's it. Particularly in New England where you get road salt. You get a little road salt splash up in the winter up onto your battery terminals. And the anode, where the corrosion occurs at the anode, will form these lead carbonates. The other one is cathodically protected. Okay, that's why it only occurs at one of them. All you need is something that will dissolve lead carbonate, but what you really want to do is rinse it with a lot of clean water to get rid of the chlorides, because it's the chlorides there that are just running around and spinning off lead carbonate and crudding up that terminal. Well, the same thing occurs if you have a flux on a printed circuit board and there's any humidity around, and you get any chlorides from residue left over from the soldering operation. And remember, chlorides really help that acetic acid wet the surface. A lot of applications will require that you have 0 chlorides in your flux. A lot of the critical soldering applications, because they're worried about this. Also, when we make semiconductor chips, a lot of times you put the chip right on the board. We talked about C4, you know, the ball bonding and stuff. You have to basically put something over that whole thing because now we've got very small joints. Okay, these wires, remember the tab wires, like 1/1000th of an inch. It doesn't take much corrosion to violate that 1/1000th of an inch. And so they have basically polymer-based encapsulants. You can't just leave the silicon chip just sitting proud on the board. And one of the things they have to do, they had a big study here a few years ago with IBM and some others, with some people in polymers and corrosion, looking at the permeability of moisture and chlorides through different types of polymers. So you get an encapsulant that keeps even small amounts of stuff from getting through to the chip and causing corrosion. Because that's basically how things fail. In fact, if we talk failure, have any of you heard of the bathtub curve? Oh, okay, well, this comes out of the AT&T Reliability Handbook. And the bathtub curve looks like that. Looks like a cross-section of a bathtub. They call it the bathtub curve. This is the number of failures over time. And this over here is called infant mortality. And this is called old age wear out. Or corrosion, wear, corrosion, or whatever. And this is the steady state failure rate. So it turns out if you have a manufacturing flaw, if you have a defect in the way you assembled it or the material that it was assembled from, it will cause infant mortality. The thing's going to fail in a fairly short period of time. Different components have different lifetimes. So something might have a 30-year lifetime, something might have a 1-year lifetime. But you'll have a high rate of failures initially, and it will drop off typically to some steady state rate. And the old age wear out is when corrosion and everything else, when you start to see the rate increasing, you know it's time to replace whatever it is. And that's basically what we do with our automobiles, right? Here's your infant mortality, warranty repairs. Why are they warranty repairs? Because they were created in the factory, okay? They got to fix them because they screwed it up in the factory. After a certain amount of time, well, you're in here at steady state, and yeah, there's a certain probability, but it wasn't that they did a bad job, so they're not going to cover it under warranty after a certain amount of time. And old age wear out, well, when it costs us more to fix it all the time than to buy a new one, we scrap it, right? So it sort of makes sense. It's actually common sense when you think about it, but there actually is a manual, I guess I could have brought it up, that AT&T started looking at this stuff in 1925. They were way ahead of everybody else in the world. And they actually have something called FITS, which stands for failures in time. And one FIT is 10 to the minus 9 failures per hour. So if you want 1 part per billion per hour failure rate, and if there's 10 to the, let's see, around 10 to the 4th, 8,000 hours in a year. So just call it, they always use 10 to the 4th in the AT&T book, okay? So if I had 1 failure out of 10,000 in a year as my steady state rate, that would have a failure rate of 1 FIT, okay? 1 in 10 to the 4th times 10,000 hours in a year. So if I had 1 failure per year. It's sort of interesting. You know, you may have a solder joint, and the solder joint may have a probability, let's see, a failure rate of 10 parts per million per year. So you'd have 10 solder joints fail out of 1,000,000 in a whole year's time. I mean, solder joints are reasonably reliable, but they will fail. But then you get to something like a lamp, a light bulb. Turns out it depends on the type of light, whether it's a fluorescent or an incandescent, but the failure rates start to get much higher, right? If you start thinking about it, in a year, or actually in 3 years, I mean, very few, it depends on how much they get used, but very few light bulbs last more than about 3 or 4 years if they're being turned on and off in your house. I mean, just think about how often you have to replace light bulbs, right? I remember the one that surprised me, but then I started thinking about it, was the failure rate of motors is 5% per year. Now you guys probably, you'd say, well, it seems like too low, but when I saw 5%, I thought, that's pretty high. But if you think about it, that means all your motors are going to fail in about 20 years. It's a 20-year lifetime on a motor, right? Of course, a motor is a little more complex than just a single simple solder joint. In fact, there's multiple solder joints in there. And that's one of the things about the whole reliability handbook, is they go through and they say, well, you can actually calculate, if you know the reliability of each individual component, you can calculate what the reliability of the overall system is going to be, which is not too hard to figure out. And that's why all you guys are always saying, keep it simple, right? The complex systems never work, okay? I remember a guy from Xerox used to talk about the instrument swamp. Is you kind of people who like to have, let's say it's an audiophile, someone who likes fancy stereo equipment, right? And they got all this stuff. In fact, actually, I have an even more recent example. Last night, my daughter called, because the beginning of the week, her husband started his dental practice. And things have just been a mess this week because the DSL didn't come in on time. And he basically has a high-tech office where you take dental x-rays, and I guess they don't even have film. It just directly gets input into the computer, and so he can sit, you know, the technician can go take the patient's x-rays in one room, and he can just pull it up on the x-rays up on the screen in the examination room where he's doing the work, you know, and stuff, except nothing worked. Right? The computer, I mean, when you didn't have the DSL system to network everything, I mean, it wasn't working. And then, you know, the credit card system, you know, his first patient, you know, owed him $400 and he couldn't even swipe the card because, you the credit card thing. So I'd say, well, thanks, and we'll collect from you later, hopefully. Right? Anyway, so a little bit too much technology sounds like, but anyway. Okay, let's talk about brazing. Unless you have any questions, we spent more time than probably needed to on soldering, but we're going to go very quickly through brazing because it's the same thing as soldering. Maybe I should have started down here anyway. Brazing is just a higher temperature, but because we have higher temperature, it gives us another opportunity, okay? Opportunities. So brazing, the higher temperatures mean, number one, more brazed alloys. Remember, there's only so many metals that melt at low temperatures. I have a much much larger choice of brazed alloys because I've got more things to work from. More fluxes. Well, in soldering, I said you can't solder titanium or beryllium. If you learn how to do it, let us know. In fact, you can if you plate them with something else that you can solder, but you can't solder directly to them. And so when we have to solder titanium or beryllium, we basically have to do something plated. Or I gave you the hafnium example where I put some nickel on the surface and then I could solder to it. It turns out because of the higher temperatures, I can get more aggressive fluxes, and I don't know of any material that will take the brazing temperatures, which are above 425 C, that can't be fluxed. I've never run across a material that can't be fluxed with something, okay, as far as that goes. So it turns out titanium can be brazed just fine. Beryllium can be brazed just fine. So because I have more reactive fluxes, I can braze just about anything. And that means I can braze not just metals, I can braze ceramics, I can, or any other high temperature materials such as ceramics, okay? Another thing is the room temperature strength of the joint increases over soldering. And soldering typically, I mentioned before, is about 1,000 psi is a typical joint, solder strength joint. In a braze, just to give you a typical number, it's 5,000 to 10,000 psi. Soldering, in fact, my more specific rule of thumb, which I guess I've looked at data before and some experience in seeing failures, a solder joint will creep if you put a low stress on it over time. The metal will flow because you're at a high fraction of the melting point, of the absolute melting point. And my rule of thumb is if you're 100 degrees centigrade below the melting point of the solder, you can apply about 1,000 psi, but no more over a long period of time. If you're less than 100 degrees below the melting point, I don't know what you can apply. It really is going to get very alloy specific, but it's going to be less than 1,000 psi. And you probably don't want more than 100 psi. You may not want more than 10 psi on the solder joint. And so there's all kinds of things that people do. In fact, I guess maybe if I remember on Monday, I'll bring it in. I've got a sprinkler head in my office, okay? You know, the fire sprinkler heads. And they actually use a low melting solder, but they do a number of things to reduce the stress on the solder joint. The solder joint is the thing that is going to be the temperature sensor that's going to let go when it gets hot. You use a solder that melts at 160 degrees Fahrenheit or 212 degrees Fahrenheit or whatever. But you don't want, and they basically, for fast-acting sprinkler heads, they use very, very thin, I don't know if it's steel or copper, whatever the metal is, just some sheet metal about 4/1000 of an inch thick with a solder joint in between, and that gives very low thermal mass to the part that has to heat up in the fire, and so it'll have a good fast thermal response because it has low thermal mass. And you've got the solder joint with a lot of solder area, but they still put tabs, ears on the ends, so that you actually have mechanically being held together as well as soldered together, but the shear stress is being absorbed by tabs, metal tabs like this. You don't want a high stress on the solder joint because after 30 years the thing could let go and you'll have a flood when you don't have a fire. Okay, so 1000 psi when you're at least 100 degrees centigrade below the melting point. What's a typical strength of an adhesive bond joint? Well, they're all over the place depending on the quality of the adhesive bond and the cleanliness of the surface, the type of adhesive. But a good adhesive bond joint might be 2000 psi. Okay? It could be 5000 psi in some cases. Braised joints are typically 5000 to 10,000. I have seen braised joints at 40,000, and we'll talk about how you can get some higher strength braised joints. But just in general, don't rely on making braised joints on a regular basis at 40,000 psi. Okay, you can't match base metal strength in most cases with just bonded just by a simple cross section in a tensile specimen. You usually need lots of surface area, so you need overlap on these things. So okay, so we got strength is better. We've got another thing which is not necessarily a good thing, is you've got to worry about volatilization. Okay. Of alloy elements. I'm at higher temperatures, and so now I'm going to have problems in silver solders. One of the best alloying elements you can put into silver solders, just like lead tin solder is one of the best solders for true soldering of electronics and stuff. One of the best brazes in silver, for silver brazes, are brazes that contain some cadmium. Now, cadmium is toxic. Cadmium has a fairly high vapor pressure, and in fact, in the 1980s, they were trying to remove cadmium from the environment entirely for toxicity reasons, human health reasons, and everybody said they were going to outlaw cadmium in silver brazes, and they never could. We still use it, but with very stringent controls and hoods sucking the air away to make sure the operators in the factory don't get cadmium poisoning. But in fact, cadmium just lowers the melting point, improves the flow, just has all kinds of operating characteristics that make it so much better for silver brazing that we actually, in the 1990s, we started seeing an increase again in the amount of cadmium-based silver brazes. We have silver brazes without cadmium, but we're going back to using it a lot. The Swedes were some of the strong environmentalists and wanted to get rid of cadmium. And it turns out I just created some cadmium vapor in the room by turning the lights on and off. Every light switch has got some silver oxide contacts, electrical contacts. It's only 0.1% cadmium oxide, and it turns out that you have silver contacts because silver is a good electrical conductivity, good thermal conductivity, and I can carry currents up to about 5 amps with just straight silver contacts. But if I want to get to 15 amps, and guess what rooms are rated for, 15 or 20 amps, I need to add a little bit of cadmium oxide, about 0.1%. Because it changes, and people are still studying exactly what it is, but it changes the electron emission, and so when you open and close that switch, there's a tendency, actually when you open the switch, there's a tendency due to the inductance in the electrical circuit to draw a little arc for a fraction of a second, okay? A very small fraction of a second. Well, cad oxide helps quench that arc and stop the arc from continuing. Okay? It makes a much more effective circuit breaker. You can triple the current that you can use on your electrical contact by adding 0.1% cad oxide. And so theoretically, I don't know how many 3 or 4 CAD atoms probably got released just then, right? Of course, they also probably condensed inside the switch. Okay, they didn't get out here for us to breathe necessarily. But the Swedes were so worried about this that they basically, in the 80s, outlawed cadmium in electrical switches. And then they found they were burning down so many houses that they finally thought, well, maybe we will allow cadmium oxide. And so they had to get rid of their environmental law. It was a stupid law anyway, because the amount of CAD oxide that's in there and the amount that gets vaporized from turning a switch on and off, it's ridiculous. It's people who don't understand the science, okay? Anything that's toxic, it's the dose. Actually, the guy who's the father of toxicology, and this is going back 400 years, I can't remember his name right now, but he said the dose is the poison, although I think he said it in German, whatever his nationality was. But he said the dose is the poison, okay, or the dose makes the poison. And I've always said, even before I heard that, if you eat 10 gallons of ice cream a day, probably will be toxic, okay? Now, obviously, some things are toxic at very small levels, and that's why we have to worry about them. So anyway, volatilization of alloying elements, cadmium, magnesium, zinc, okay? Zinc, when I get to melting temperatures of some of the brasses and stuff, or even brazing, if something has a fair amount of zinc in it, you can vaporize zinc, it forms zinc oxide in the air, you breathe in some of the zinc oxide, and you get what's called metal fume fever. And I've never had it. I've talked to some people who've had it. I remember a technician who trained me around here. He says, first you get so sick you're afraid you're going to die, and then you get so sick you're afraid you're not going to die. But it only lasts for about 24 hours. But you start getting high temperatures and chills and everything if you breathe in too much zinc. Now, it turns out zinc is not really toxic. I think we talked about that the other day, that they actually use a vitamin supplement. So it's only if you get an acute high dose, by inhaling, you can get metal fume fever from zinc. It has no long-term toxic effects. It's actually used in the body for other things. But if you get too much by inhaling, you can get very, very sick. And I have talked to some people who worked in foundries or were brazing something that had a lot of zinc or something, and they didn't have good enough ventilation and they got metal fume fever, and they tell me it's a very unpleasant experience, okay? You just get nauseous and high fever and everything. Magnesium is also, hey, we eat Phillips milk of magnesia, so it's not necessarily toxic, but it can create problems. Actually, some of these things, like magnesium and zinc, if they're in a brazed alloy, you can't always do furnace brazing. For example, or vacuum brazing. We sometimes use a vacuum to braze the thing to get rid of surface oxides and heat things up and boil, essentially vaporize off, sublime off the oxides. Well, you may also sublime off the magnesium and zinc in the alloy. And if you do that, you've got a problem. And the problem that you have is that, well, you can mess up the composition of your alloy. There are some aluminum alloys that if you try to laser weld them and you're getting to very high temperatures, you can actually lose like 1% of your 4% magnesium, and you have a lower strength weld metal because it doesn't have as much alloying element. That's higher temperatures than brazing, but nonetheless. The real problem for this in brazing furnaces is that if it gets into the windings, you now have magnesium or zinc alloying with your electrical windings of your furnace, and it will melt the windings. And there have been a number of people who said, oh, I'll use this furnace for brazing, and they start using the furnace for brazing, and a couple of weeks later they find that they have to replace the whole furnace because all the electrical windings got destroyed by the vapor coming off the braze. To make brazes, we're adding metals that will depress the melting point, and the point is some of those end up having high vapor pressure. Another problem, which you actually have in soldering as well, but it's a bigger problem in brazing, is intermetallics. And I actually gave you the example of that, the cross-field amplifier, where they were using the gold nickel braze alloy, and they were brazing molybdenum to copper, and they were getting nickel 3 molybdenum, which was a brittle intermetallic. And with that particular braze alloy, they could get like a 2 2-degree bend before the thing would snap in a brittle manner because of the brittle intermetallic of nickel-3 molybdenum. So you've got a gold nickel braze alloy. The nickel in the braze alloy reacts with the molybdenum base metal, forms a brittle intermetallic. And they got around that by dropping it from 18% nickel to 3% nickel. They didn't form the brittle intermetallic, they formed a TLP bond, and they could take those things and bend them 90 degrees or 120 degrees without breaking. Another problem, since we're at higher temperatures mean higher thermal stresses. Actually, one of the advantages of solders is because they do creep, they often relieve some of the thermal stress at the interface. In brazes, I can end up with thermal cycling, actually getting thermomechanical fatigue because the material does, has enough strength and is not in the creep regime at room temperature. Another is erosion of the base metal. I'm at a higher temperature and therefore I have a tendency to erode the base metal more. And to give you an example of that, which will probably be my last example here. This is part of the shroud of a jet engine. And so I've got my vanes that are spinning past here. And I'm trying to, in the compressor, I'm trying to compress the air. And on this side of the vane, it's not high pressure. On this side, it is high pressure. And I'm trying to compress it so I can combust the air. Well, it turns out that as I spin past here, some of the gas could leak out over the top, and I'd lose efficiency in the engine. And even a few thousandths of an inch is enough to degrade the efficiency of the engine, and I want high efficiency in my engines. So what do? I have to form a seal. And well, I got another problem. These things are going to creep over time. They're operating at high temperatures, and they will slightly elongate. They may elongate by 2 or 3% in length over their life. And if they're a couple inches long, 2 or 3% is a millimeter. So what do? You essentially make a honeycomb of metal and braze it to the substrate. And now this thing has something that will form a seal. It will rub up against it, and it will basically just eat the honeycomb away without hurting the blade. In fact, sometimes the blades, this one doesn't have it, actually this one's been cut off. A lot of times the blades will actually, they will braze on carbides on the top so that it can eat its way into the shroud, okay? But it's often a honeycomb, and you're just doing that to prevent the backflow of gas in your compressor. So that is an application where you have some very thin material, and if you have very much erosion in your braze, when you make the braze joint, and this thing starts out at 5 thousandths thick material, if I got 2 thousandths erosion on each side as the braze alloy dissolving some of the base material, I'd have a problem. I wouldn't have much left. And so it turns out, next time, we've run out of time, but I'll tell you, I might tell you a story about how this is an application where 25 years ago they used to use the gold nickel braze alloy. They don't anymore, but they did. And it was a fairly high cost area of the fabrication of that engine.